非常感谢这一次来自 Viavi 的3位嘉宾，以及在座参加研讨会的各位。那我们现在以热烈的掌声欢迎我们的上半场讲师 Gex。
大家好 but really talking about driving functional test. So rather than testing individual units as you go along, we're trying to get as much test earlier in the stages so that you know, have a predictability in yield and performance at the end of the line. So let's just talk about CPO. I'm sure many of you will have seen slides similar to this, but let's just sort of go back to it. You know, what is CPO? Stands for co-packaged optics. So in the same package, you can take an integrated circuit. You have optical modules and external laser sources. All of these are co-located within the ASIC. You can see here, this is an example of how it would be built up. It's a fairly complex device. And what I could say, you know, a lot of this silicon photonics and CPO technology feels to me, you know, I've been in the industry a long time. 25 years ago, we were building WDM networks, and it was all new, and we had nothing to test it. And I think when it feels like that stage now we've got, I think, a lot of technology in the silicon, and a lot of tests along the way, and a lot of it's going to require new solutions and scalable solutions. And I think that's where we've got to get to, is not just the new testing, what are you going to be testing, how often are you going to be testing, what really matters in production, but and how we're going to get the scalability as you go along. Many of you will come maybe from the silicon industry. We've obviously very strong in photonics. So we can match that expertise between you having the silicon expertise and us having some of the optical expertise. We can learn more about the silicon processes and the silicon attributes, which we can help, and we can help you with the photonic test side of that. So we are very strong in the photonic test. So, I mean, we've all seen curves like this. We've seen, you know, shares of NVIDIA go through the roof. It's driven a huge amount of transceiver production. And Paul will talk a little bit more about this later in his presentation. But you can see here, all of this AI data center driven growth is driving huge volumes. Look at the growth here of 23 over 24. It's a huge percentage growth. And what we're seeing is what we predict, or what's being predicted by 2030, is that the proportion of CPO is going to make it's going to be a bigger proportion of the business. And it's probably the only solution for scale-up multi-rack systems. Okay, so why CPO? Clearly better signal integrity, lower power requirements, and faster communication. And you can see here, there's the ASIC here, and underneath here are the connections through these FAOs. And I'm going to talk a little bit about FAO connections later. On the outside of this, and I'll show you a box later, but a lot of these FAOs are what I would call private labeled in a way. They are generally unique and very different. There is not one standard FAO. So there's a complexity that you guys have to overcome to be able to test that. And more importantly, you need to inspect it as well. You've got to make sure it's clean. You've got to make sure everything's in the right place before you attach it, and you're not going to have any issues. This is a fairly complex device here. And then when you get to the box itself, this is the NVIDIA box, InfiniBand. These are all MPO connectors. If you just look at the modest projections of growth of CPO, there are going to be 30 million MPO connectors needed to satisfy that demand. That's a lot of connections, it's a lot of inspection, it's a lot of cleaning, and it's a lot of tests. And then behind that, if you were to open that box up, you would see the fiber ribbons coming through there, and each one are labeled, little plastic labels. Tapping stuff has actually to take that and physically connect it to the reactor. How are you going to make sure that you've connected everything correctly? So there are test methodologies that you use to make sure that everything is connected as it should be, so that when you put it in the rack, it will work as you predict. This is just the Broadcom version of the device, all very similar, but again, you can see the amount of fiber coming out of this. So there's a huge amount of fiber play based on this. And then you've also got the difficulty of when you're actually building these silicon photonics chips. How can you test on the wafer level? And what matters is here is you're looking, even with these connections, you're looking at 3 to 5 dB of loss. So higher powers are needed to be able to test chips, higher dynamic range. And then, of course, you've got to do this fast. This can't be slow, it's got to be fast, repeatable process with difficult connection technologies. So power is needed, dynamic range is needed, and speed is needed. And then when you look at the ecosystem, and there will be many of you here who are going to play into this ecosystem at various points. Clearly, there's the module assembly itself that has to be assembled, then put into the box, and then connected with the right connections, which we showed you earlier. And then, as you go down into the system, you've got your silicon photonics here, where you're looking at cleaning, inspecting, electro-optic test, packaging. You've got your appliance testing, where you're looking at optical validation. Simple, you're just making sure you've got the right connections. And then it's 30 million. Think of that, 30 million connections a year of these MPO connectors needed to be tested. They need to be inspected. And then these are remarkably difficult to test, the fabs. And all of those are connected onto this chip here. And then you've also got the EOS FPs, where you've got to clean, test optically. So there's a whole ecosystem that goes into this, that drives into the SCO. So what do we mean by driving functional test closer to the chip? You know, I think it's fair to say these photonic chips are becoming more complex, significantly more complex than we've been used to. They're not just simple waveguides anymore. You've got the test process that's co-evolved to ensure that they pick performance, and then reliability, and ultimately reduce the development and manufacturing costs. So I think there's an opportunity here, not just to characterize what we have these 2 parameters called parametric test and functional test. Parametric tests where you measure maybe insertion loss, polarization dependent loss, TM, or waveguide sensitivity. And then you've got the functional test, which is getting more be tested as a closest to what the module would be. So there's an opportunity here to move functional tests earlier in the process. That can reduce test time, it can reduce the number of test steps, and it throughout transformation. So I believe there's 3 quick requirements here. There's test module depth and flexibility, path density, parallel operation, and automation and triggering. Notice this, if you integrate chips with all those values, the parallel operation is really important, and that's going to get you the scalability. So within Viavi, there's lots of us working in this ecosystem. Within what we call our lab and production division, we've got our optical transport colleagues, our PCIe colleagues. We've got the fiber optic photonic test, which is the division I'm in. And then we've also got part of our material science group, it's called OSP, where they're doing a lot of the coatings and a lot of the materials associated with these CPOs. So we're doing a lot of co-development with them. And what I'd like to get into a situation is that, when we look at our testing and, we have a large toolkit that's available for testing. And what I'd like to do is work with you and the teams in this room to be able to figure out, okay, what is the optimal test? And everyone will have slightly different view of what the optimal test would be, depending on your circumstance, but what that optimal test would be for you. And we can work with you on, an ideal solution to that, and even do some development of our own products to be able to get you to that state. So if we look at the simplified view of the test flow, you've got the wafer test. This is where you've got the pre-singulated chip, fabrication test, fiber alignment, waveguide response, electro-optic response, and spectrum. So this is the sort of parametric test that you're looking at. No functional tests usually at the wafer level test. Then you've got your packaged device. You've got the singulated chip on carrier. You've got fiber attached. You've got hybrid material integration. You've got wire bonding. Here again, you're going to be doing some testing like the fiber attached integrity, which would be insertion loss and return loss. And then as you come up to the module, you've got the DSP integrated in the module system. You're looking at external connectors, splicing, power tests, and signal continuity. At the functional test level here, at the packaged device, you've got TX, power spectrum, return loss, signal continuity. At the module level, you're looking at bit error rate, OSNR, TDQ, telemetry cal, power and spectrum. How much of this testing can we bring sooner into the process? And how much will that save you in the number of steps going forward and your yields and your throughput? So we have two types of tests here. We have parametric versus functional tests. And the parametric test, this is the measurements taken to characterize key physical properties, like wavelength guidances. So this would be using something like what we call a swept wavelength system, where you would be sweeping the laser, you would be measuring the response of the waveguide and inferring insertion loss and polarization dependent loss, TE mode, TM mode. It would give you your waveguide characteristics based on that test. That needs to be fast and accurate with high powers and high dynamic range. So this gives you an indication of device geometry, material quality. So, have you got a lossy waveguide structure? Is it performing exactly as you would wish? And then on the functional test, what we're looking here is to assess the overall performance driven by the final application. Compliance to the linked network loss, complex device interactions. How much of that higher level testing can you bring closer to the chip? And that's what we are working with some of the people in the industry to get a more functional test lower down in the process. So parametric test measures the physical properties, the waveguide losses, and then you've got functional test, which measures assesses the overall performance that would be close to the final application. How much of that can you get close to the chip? So what we have at Viavi within the group that I work with is called our MAP platform. It is a flexible photonics platform. We call it the MAP-300. It is one platform that is used for all applications. So this can be used for anything from simple insertion loss, return loss testing, all the way up to complex, coherent device testing. So the sort of thing here, we've got waveguide characterization. This measures loss, polarization, dependent loss, responsivity. You can see here, this is what we call our swept waveguide system. It's very compact, it's very fast, and it's powerful. So what we have here is a laser, a sweeping laser. This continuously sweeps at 100 nanometers per second continuously. In this one, we have our referencing, our telemetry, and polarization capability. And then this would then go into your device, and you get the parallel, and then now you can have the parallel testing of all the inputs. So it's very, very fast, very highly parallelized. Today, that is predominantly used for making wavelength selective switches and ROADMs, and now is becoming increasingly important to the silicon photonics characterization, particularly at the waveguide level. So this is where we have capability now that's in the CNL band, and we will be launching later on this year an O-band capability for our SWS system. So this will scale from R&D to operations, span line, packaging, and final tests. And then you've got your active device and module tests. This is where you would measure your spectrum, your power, your gain, your continuity, and your single impairment. And these configurations will be generally different, so that there's no two vendors would necessarily have exactly the same piece of equipment. But nevertheless, the whole has the same functional elements. And those functional elements would be some sort of source. You've got maybe some spectral measurement, optical spectrum analyzer, some power measurements, and then all important switching, power meters and attenuators, the basis of optical tests. These can be highly parallelized through our switching, and they can, we've got different functionalities that can be used. I'll give you the functional blocks in a minute. Let me go to the functional block. Let me get the functional blocks first. So in terms of functional blocks, you have essentially all the optical, basic optical functionality you would need to your testing in these 4 blocks. The 4 blocks are sources and amplifiers, power, loss and spectrum measurement, switching and routing, and signal conditioning. So basically create light, measure light, make sure you get light to the right place, scalably, repeatably, and then you've got signal conditioning. So this essentially messes with the light. So in terms of an O-band capability here, so we have full O-band capability in all of these functional blocks. So a lot of silicon photonics today is in the O-band. You will hear a lot of this. So we've got O-band sources, we've got ultra-high power sources, general sources, we have beast sources, we have tunable lasers, we have this laser here, which is a sweep tunable laser or tunable across the O-band that's coming later this year. We've got full band OSA, and we've got, actually that's another block. We've got highly parallelized power meters. So that's 24 independent power meters in a single slot. We have a spectrum analyzer that is in a single slot. So it's a lab-grade OSA in a single slot in the lab. So it's really space-saving. And believe it or not, space-saving is important. Footprint in a factory is important. You don't want to be paying for floor space. And then the switching around gives you the flexibility to scale and parallelize. That can be 1 to 100, 1 by 100, 1 by an inch switches up to 176 ports. And then we also have the matrix switches, which is any-to-any connections. And then on the signal conditioning, we have attenuators with power control. Again, we have the high density versions with 12 power VOAs in single percent, back reflectors, and polarization surrounds. So a lot of functionality. Going back to the SWS system, this is a unique architecture that we have in the swept wavelength system, in that we can allow for highly parallelized operation. So this one laser, so remember the laser is the expensive part of the system. That one laser can be split and references. Remember, this is dynamically referenced every time. 3 picometers, absolute accuracy with sub-picometer resolution. We dynamically calibrated each time. And then it can be split between the different stations. So you can share the cost. And all of it could work in parallel and independent over 8 different stations. So you don't need to buy 8 different expensive lasers and what we call basically the referencing and metrology units. You don't need to buy that twice. You can share it between 8 stations. And all of these stations can be doing different things in parallel. So that gives you that scalability in manufacturing. And that's why this is the world's most deployed system for measuring WSS. 80% of the world's ROADMs and WSSs are measured with this system. We can now use this technology by working with you in the silicon photonics industry to bring that scale to the silicon photonics solutions. So, but there are going to be some changes needed. So I mentioned our move to O-band. So we've got an O-band capability, and that will be released this year. And then we've got this ability to mix current and photonic inputs. So sometimes in the silicon photonics chips, you're not going optical to optical, you're going optical to electrical. So in which case you need the ability to have an electrical input into the SWS while your laser is shooting. So now you can get the optical performance and you can get the spectral performance with an optical to electrical device. And then this gives an example of a DR8 switch. DR8 system. This is when you build up, you take those basic building blocks, and we can now work with you on your specific requirements to build it up into a solution. So the solution here is you have your DUT, you have your source, and then what you can do is you can build up the blocks here. So you've got a VOA times a 1x2 switch. You've got another switch, and we've got this ability called a down switch, and then to an OSA, optical amplifier, and filter, and then you get into your scope. So now with this, because we've got these 8 parallel paths, we can manage that in a single unit. So you're not having multiple units, multiple devices to talk to. All can be automated through skipping. So very easy to automate. Each one is individually addressable. So there's many variations. So not one will be the same. So there's a lot of strong dependence on end use and yield points and what different architectures you may be using. So you've got here you've got integrated VOAs with OPMs that drives functional density with functional integration. You've got loopback with your test access. We've got PM fiber capability in our switching. And then the gain option simplifies the TDQ. So one thing that we do have that is relatively unique, we do have an O-band amplifier. Now the O-band amplifier is not a semiconductor or optical amplifier. It is based on bismuth fiber. So that gives you gain down into the 1270, which is fairly unique, which your Presidinium amplifier will not give you. So we get high gain, low noise figure across a broad spectrum with this technology. So many variations are possible. You can go into many factories in the world and you'll see, or many of the optical factories in the world and you'll see lots of these systems. They may not be the same in each one, but essentially it's got those same building blocks. The attenuators, switches, the OSAs, the amplifiers, and the batteries. All of them in these mainframes. And density matters, scalability matters, throughput matters. I believe that is going to be even more important in the silicon photonics and CPO architectures. because yield, the cost per test really matters. And that's where the scalability comes in the fact that it is 8 parallel lanes being tested in the same. So you see here there are 8 lanes. You've got this VOA, which is 8 VOAs in a single slot. You've got 2 quad sources, which would be here. Your 2 E/8 switch, which allows you to switch to the OSA. You've got your O-band amplifier. You've got your ASC filters, and then you've got your optical spectrum. So all of that functionality times 8. Remember, this is 8 lanes all being tested, can be fit into a single chassis. And then the other thing that's important when we talk about, optical alignment, we talk about all the parts that are going into the CPO. Triggering is very important. We now have the basic architecture within the MAP platform to be able to support triggering. And then as we are learning and hearing, we are adding functionality to the devices. We've got the architecture, and now we need to be able to add that, the triggering to each of us. So we've got these trigger modules with LXI and SMA connections, and you've got the ability to trigger on OPMs have triggering, our VOAs have triggering, our OSA is going to be having triggering. So as you're doing your alignments or any of your structural stuff and you may want to be on testing, you maybe want to use this triggering capability. We have all. And then we talked about the highly parallelized nature of that system. You saw all those FAO connections, you saw all the NPO connections that are highly parallelized. We have the high density capability in our power meters that allow you basically to do alignment and switching applications. So these can be internally or externally triggered. But this is basically an OPM scope, taking, you can have up to 96 power meters all connected in a chassis, driving, logging, and charting changes. And then all important, all of this can be ruined by dirty connectors. Believe it or not, if you do not clean your fabs, if you do not inspect your fabs, if you do not clean your NPOs, you will not have a working device. It's as simple as that. And the number of times I've been in test application engineers and people will say, hey, everything's not working and can't get it to work. You go back, sometimes you've just got faulty connector. It's as simple as that. Make sure you connect them, inspect them, make sure you clean them, make sure you do nothing. So we do have all the inspection and the cleaning capability that you would need. So here at the front panel, these are what we would call our public connectors. These are fairly standard NPO type connectors or C type connectors. Then you go into another breakout with NPO, ribbon fiber, and then this pod connector. This is where you're going to get some unique and very different capability, different types of devices. So those fabs, as they never really, I've never seen one the same. They're either a different length, or they're a different type, or they're a different angle. We have this capability now that we've got this device, this universal adapter that has an insert in it that you can now do your own printing, 3D printing based on your fab. So you can keep the same clamshell. You can do your own 3D insert. We'll give you the dimensions and the material to be able to make this. And then you can pop it into inspection, into cleaning, and into the power meters to do our insertion loss, return loss. So all of that is really important. Connections all the way, because these are all multiple points of failure. So make sure that you have it all clean. And then I mentioned the measuring of the short DUTs. So a foul can be quite long. Sometimes they can only be a few centimeters. This one here is a dual foul. One at 45 degrees, one at 7 degrees. You can see that that's what, less than 3.5 centimeters long. That's a very small device to handle, to move around and to measure. So you can measure the insertion loss of it fairly straightforwardly, but then how do you get this, measure the output at this end, or how do you connect to this end and measure the output at this end? You've got to have an adapter. So we are developing new types of adapters, and these new types of adapters will accommodate these angled connectors, the short fouls, the very short devices. So now you can get insertion loss and return loss of that device. Remember, you can't get return loss of one end versus the other. You would get return loss of the entire device. In summary, what we've got is we're really driving functional test flows to the chip. I mentioned earlier, we've got the parametric test that measures the waveguide, structure and material quality and integrity. And then you want to be able to bring some of those higher functions closer down to the chip so that you can improve your yields, reduce the number of steps. So there's opportunities to do that. We want to work with you on that. You have all the expertise in the world in silicon. You have all the expertise that you may need in photonics. We don't really know anything about silicon, and we're learning about silicon photonics. What we can do is we do know about tests. We know a lot about this. And so this feels a little bit like the early days of WVM, when there was no test equipment around. There was no standard way of testing WVMs in the early days, so we had to create our own ways. And I feel that this is the next, where we are today, is that we're going to have to work together to find these new tests, new ways of bringing those functional tests closer to the chip and earlier in the process. New ways of cleaning, new ways of handling, new ways of inspection. So we would like to work with you proactively and on these solutions. So we've got test module depth and flexibility, path density, and this parallel operation. I mentioned highly parallelized operation. And then this automation tree. Automation is involved. You're going to be in these big pro stations, maybe where you're looking to do the testing, you've got automated handlers. It has to be automated, and it has to be parallel, and it has to be fast. So that's the summary. Thank you for your attention.